assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
For this problem, there is a block attached to a string that has a spring constant of 400 newtons per meter. It is at some point in time where the position from the system's equilibrium, the velocity is negative 13.6 meters per second. The displacement is 0.1 meters per second, and the acceleration is negative 123 meters per second squared. And we're being asked to figure out what the frequency of oscillation, the mass of the block, and the amplitude of the motion. So for the first part, finding the frequency, we can use the equation acceleration equals negative omega squared times position, and we're going to actually replace the term omega with 2 pi f. So we will end up with acceleration equals negative 2 pi f squared times position. And we can also now substitute in our known values. So we know that we have our acceleration is 123 meters per second. We have our negative 2 pi. We're just going to solve for f squared, and we know that our position is 0.100 meters. Rearranging this to solve for f, we would have f equals square root of 123 divided by 0.100 all over 2 pi, and that would give us a solution of f equals 5.58 hertz. Our next task, so now that we have that our f is 5.58 hertz, we're going to try and find the mass of our block, and we're going to be using the equation K equals mass times omega squared. So we have our K, which is our spring constant, is 400, equals mass is what we are trying to solve for. And again, since we know our frequency, we're going to substitute in 2 pi f, which is 5.58 hertz squared. So that will give us, when we solve for m, we end up with 400 divided by our 2 pi 5.58 squared. And that gives us a mass value of 0.325 kilograms. The final part of the problem is finding the amplitude, and so we're going to use the velocity for that. So we have velocity equals negative omega times our amplitude. We know that this is the velocity is when the time and the position is measured when it's at equilibrium, so we don't have to worry about the sign portion of this function. We can leave it just with omega xm. So we would end up with negative 13.6 equals negative, and we're going to put in our 2 pi f again because we have our frequency, times xm. And when we solve for that, when we solve for our amplitude, we end up with negative 13.6 divided by negative 2 pi times 5.58, and that gives us a value of xm being 0.4 meters.